Hello friends, in this video we are proceeding into the second section of Module 15 covering pages 533 to 537. So what we're going to proceed doing here is looking at more details on K, talking about chemical equilibrium, and we're going to look at the phases of matter of our reactants and our products, because there are some rules which actually simplify things quite a bit. If you have a reactant or a product in the solid phase, or as we're going to learn, the liquid phase, they are not included in this equilibrium equation. So for example, in this equation here, we have the sodium hydroxide in the aqueous phase, the magnesium chloride in aqueous, magnesium hydroxide in solid, and the sodium chloride in aqueous. Because this is in the solid phase, it will not be included in our equilibrium equation. So for our products, which is, remember, go always in the numerator, we're just going to use the sodium chloride. And once again, we look at the stoichiometric coefficient, the 2. That's the exponent that is used to raise this concentration to. And then for the denominator, we'll be using the magnesium chloride of the reactant and the sodium hydroxide. They're both in the aqueous phase. And once again, you check the stoichiometric coefficient, and that's going to be your exponent in that equation. Now in the second chemical reaction, we have an example of when you have a liquid here. So here we have the hydrogen peroxides in the aqueous phase, water's in liquid, and oxygen is in gas phase. So we're not using the liquid to calculate K, but we use the product of the oxygen gas in the numerator. Since there's no written stoichiometric coefficient, this is just without an additional exponent. And then the hydrogen peroxide is in the denominator, and the 2 here is our exponent for that. Okay, so let's look at an example of this on 15.2 on page 535. Just as a small review on the side here, we'll look at the difference between ammonium, which starts as a polyatomic ion, it's NH4, versus the NH3, which is ammonia, this is always typically found in the gas form. So it says, what is the equation used to calculate the equilibrium constant in the following reaction? So we have the ammonium chloride in solid phase, the ammonia in gas, and the hydrochloric acid in the gas phase. So, as we know, we are not going to consider anything in the solid phase. So, interestingly, for this one, we're just looking at the products, and so we just have the concentration and equilibrium for these two products multiplied out, and that would be our K for that reaction. So here's another chemical equation. And some of our reactants and products here are, this is acetic acid, the CH3CO2H, that's in the aqueous phase. Then we have ethanol, is the C2H5OH in aqueous. Then for our product, we have ethyl acetate, that's CH3CO2, C2H5 in aqueous. And then finally the H2O in liquid. So our take-home point here is that we're not including the liquid in our calculation of K. For the product, we're just using this product, which is the ethyl acetate in the numerator. And then for these two would be the concentration of these is included in the denominator. Okay. So on your own 15.5, it says, give the expression for the equilibrium constant of this reaction. So we really are focusing in these cases on the phase of each reactant and product. So we have solid, liquid, aqueous, gas. So we've learned that we are not including the solid or the liquid in the calculation of K. So we're only, in this case, using the products, which are aqueous and gas. So we have the product of the lithium hydroxide, so that concentration's included, and the 2 is our stoichiometric coefficient, which is then used as the exponent, and then the hydrogen gas is the concentration here. All right, another on your own, 15.6. It says, what's the equation for the equilibrium constant for the following reaction? So here we have some interesting reactants and products. This is called barium hydroxide. You can see the hydroxide group here. Octahydrate. So that's the octo means 8. Then we have, this is ammonium. Remember that polyatomic ion. And this group is called thiocyanate. And then they sort of flip-flop. And now we have ammonium hydroxide and the barium thiocyanate. And then obviously that's water. So let's look at our phases. We have solid, solid, aqueous, aqueous, liquid. So the only 2 that make the cut for the K are these 2, because they're in aqueous. We don't include liquids and we don't include solids. So here we have the ammonium hydroxide. Since our stoichiometric coefficient is 2, our exponent is 2. And then with the barium thiocyanate, since there's sort of an invisible 1 here, that's just given that it's that concentration. All right, now I'm sure all of you sitting at home are wondering, how can we tell if a reaction has reached its equilibrium? Right, that is a fascinating question, and you don't have to wait any longer. We're going to answer that. Okay, so let's have a look at this example 15.3. I'm on page 536. It says, a chemist is studying the following reaction. We have nitrogen gas reacting with oxygen gas, and then we have it yielding nitrogen monoxide in the gas form. So first of all, looking at the phases here, we can see they're all gas, so they're all going to be included in our calculation for K. So it says, she knows that the equilibrium constant for this reaction at this temperature is 0.050. All right, so that's an important piece of information for this problem. Suppose she knows that the concentrations of each substance are as follows. So she's giving us the nitrogen concentration, the oxygen, and the nitrogen monoxide. Now notice that they don't have little EQs after those concentration brackets because we don't know if it's at equilibrium, right? Determine whether or not the reaction has reached equilibrium yet. If it has not, determine the direction it will shift in order to reach equilibrium. So it's asking if the equilibrium's off, in order to get it to equilibrium, should it shift toward the product side or toward the reactant side? So it says, first we have to see whether or not the reaction has reached equilibrium. So first we have to calculate our K. So again, we start with our products in the numerator, the NO, the nitrogen monoxide to the second power, and then we have the reactants in the denominator. We're going to plug in these numerical values that are given here. So we have the 0.02, and then in the numerator squared, and then the 1.5 and the 1.3 in the denominator. Our units are going to cancel out because we have m squared in the top, and then it ends up being m squared in the bottom. They cancel out. So our final answer is the 0.00021. So now our question is this value, is it larger or smaller than the one for equilibrium, the 0.050? All right, so clearly this is a smaller number than the 0.050. So now there's a bit of a we sort of defer to our rules here. Since the K is smaller, since this K is smaller than the equilibrium one, then we know that in order to get this to equilibrium, this would have to increase in value, the 0.00021. And the question is, what would happen to make this increase? Well, we know if we increase the numerator, which is the products in this case, then this would increase. So the answer for which way should the reaction shift, it says since the K is smaller, then the products should increase, the products, to make the K larger, and that would shift it to equilibrium. Okay, now there's a second part of this problem. It says the same chemist studied the same reaction under different concentrations. Suppose this time the chemist measures these concentrations, so it's a new set of data for each one. Again, we're asking, is the reaction at equilibrium under these conditions? And if not, how would it need to shift? So we've set up the same formula, the products over the reactants. We fill in the values that are given here. And the calculation, again, the units have canceled out. Our final number is 50, all right? So the question is, again, is the one that we reached here, 50.0, smaller or larger than the one that was given for the equilibrium, the 0.05, all right? So clearly we know the 50 is greater than the 0.05. So now we know that in order for this situation to reach equilibrium, this would have to be reduced. We'd have to lower the 50 down to 0.05. And the question is, what would need to happen in order for that to be reduced? Well, if the denominator, which represents the reactants, is increased, if these are increased, then this value would go down. So, since the K is larger than 0.05, then the reactants, which is more or less the denominator, should increase to make the K smaller, and that would bring the situation closer to equilibrium. So the reaction must shift toward the reactants. All right, now let's look at on your own 15.7. It says a chemist is studying the following reaction. So we have ammonia is yielding nitrogen gas and hydrogen gas, and they're all in the gas phase. The reaction has an equilibrium constant of 17 molarity squared. The chemist measures the concentration of each substance, and then we're provided with their concentrations in this situation. So we have to determine if it's at equilibrium or not. So once again, our K is going to be calculated by starting with our products. Up here, none of them are in solid or liquid form, so they're all going to be included. So the products are in our numerator, again with the stoichiometric coefficient being used as an exponent here. And then our reactant on the left side is in the denominator, with this 2 being the exponent here. When everything's calculated out here, we get 21 molarity squared. And so we have to compare this number to the one given in the equation. So since 21 is larger than 17, in order for this to be brought into equilibrium, it would have to be reduced. It would have to go down. And in order for the 21 to go down, that means that our numerator would have to be increased. So the reaction should be shifted toward the reactants, which is basically making the denominator larger to reach equilibrium. It's just a mathematical analysis. Okay. So that's it for this section, and in the next section we'll be looking at a new principle.